Hello! In this video, we'll continue our exploration of integration of rational functions by partial fractions and consider an example containing a quadratic factor in the denominator. If you want to review the instructions surrounding the integration of rational functions and the rules that need to be applied, I encourage you to return to part 1 of the video entitled Integration of Rational Functions by Partial Fractions. We'll proceed with our consideration of an example containing an irreducible quadratic in the denominator. Suppose we'd like to evaluate the integral of w to the 4th plus 16 divided by w to the 4th plus 16w squared dw. The first thing we need to consider is to look at the degree of the numerator and compare it to the degree of the denominator. When we consider the degree of the numerator, we look at the highest power of w, in which case 4. The highest power of w in the denominator is also 4. Since the degree of the numerator is the same as or greater than the degree of the denominator, we must perform polynomial long division before continuing. So let's review how that works. We're going to put that numerator, w to the 4th plus 16, under the long division sign. Now I know in advance that there will be a w squared term that arises, but if you should need a w cubed, a w squared, a w term, and you don't initially have them in place, you can put them there with a coefficient of 0. We want to divide this by w to the 4th plus 16w squared, which was the denominator of our rational function. The first thing I do is I want to consider how many w4s go into the highest powered term of the dividend. We see that w to the 4th goes into w to the 4th one time, so we'll put that above this, the 1 above the 16. Then we multiply the 1 times my divisor, which so 1 times w 4th plus 16w squared will be w to the 4th plus 16w squared, and then I'm going to subtract that quantity. When I perform the subtraction, I'll get a negative 16w squared plus 16 when I bring down that 16. And since w to the 4th does not go into negative 16w squared with a power of w that's 0 or greater, I'm finished with my long division. And I know that w to the 4th plus 16 over w to the 4th plus 16w squared is equal to 1 plus my remainder, negative 16w squared plus 16, over my divisor. So I can continue with my integral. So I've rewritten w to the 4th plus 16 over w to the 4th plus 16w squared as 1 plus negative 16w squared plus 16 over w to the 4th plus 16w squared. And I'm going to perform partial fraction decomposition with negative 16w squared plus 16 over w to the 4th plus 16w squared. And first of all, I have to factor that denominator, and I notice that w squared is a factor of each of w to the 4th and 16w squared. With that, based on the rules of partial fraction decomposition, I know there will be 2 partial fractions associated with w and 1 partial fraction associated with w squared plus 16. So to set up the partial fractions, I'm going to have negative 16w squared plus 16 over w squared times the quantity w squared plus 16 equals a over w plus b over w squared plus cw plus d all over w squared plus 16, where a, b, c, and d are all constants. So next I multiply both sides by that denominator, w squared times w squared plus 16. I get negative 16w squared plus 16 is equal to aw times w squared plus 16 plus b times w squared plus 16 plus cw plus d times w squared. And this is true for all values of w. So I'm going to first let w equal 0, which will allow this term and this term to drop out, leaving only b times w squared plus 16 on the right and 16 on the left, which will let me solve for b. And I can find that b is equal to 1. When b equals 1 in this equation, I can continue and solve for a, c, and d. Now at this point, I can distribute AW across W squared plus 16 and W squared across CW plus D, and get that negative 16W squared plus 16 equals AW cubed plus 16AW plus W squared plus 16 plus CW cubed plus DW squared. And with this, I can collect common powers of W. So for example, I have AW cubed and CW cubed. I have W squared and DW squared. I have 16AW and 16. So when I group those together, I get negative 16W squared plus 16 equals A plus C times W cubed plus 1 plus DW squared plus 16AW plus 16. And I can match powers of W on both sides. So negative 16W squared will correspond to 1 plus DW squared. This 16 can be subtracted from both sides, which we'll do right now, and I get negative 16W squared equals A plus CW cubed plus 1 plus DW squared plus 16AW. Since I do not have a W cubed term on the left side of the equation, A plus C must equal 0. And in the same way, I do not have a linear term on the left side of the equation, so 16AW must also equal 0, which forces A to be 0, and since A plus C must equal 0, C must also be 0. So the only term I have yet to determine is D, and I know that negative 16 plus equals 1 plus D, so that D must be negative 17. So now I have the 4 constants I need for the partial fraction decomposition. So negative 16W squared plus 16 over W squared times the quantity W squared plus 16 is equal to 0 over W. That 0 comes from A. 0 over W plus 1, which was the B, 1 over W squared, plus C, which is 0, 0 times W, plus D, plus a negative 17, all over W squared plus 16. So I know that my negative 16W squared plus 16 over W squared times W squared plus 16 is 1 over W squared minus 17 over W squared plus 16. And if you go through and find a common denominator on that right-hand side, you should get back to negative 16W squared plus 16 over W to the 4th plus 16W squared. So let's go back to our original integral we wish to evaluate. So we've got the integral with which we started. We performed the long division, which means we've got the 1 plus negative 16W squared plus 16 over W squared times W squared plus 16. In the integrand, we now have the partial fraction decomposition for that rational piece of the integrand, and we can perform our integration. 1 over W squared can be rewritten as W to the negative 2. That 1 over W squared plus 16 suggests that we're going to have an inverse tangent as our antiderivative. And so our answer is W minus 1 over W minus 17/4 arctangent of W over 4 plus C. And again, you can check your answer by taking the derivative of that antiderivative and going back to see if that is the same as W to the 4th plus 16 over W to the 4th plus 16W squared. You may need to do some algebra and find some common denominators to make them align, but you should be able to check that work. In summary, partial fraction decomposition is an algebraic technique used to convert complicated rational functions into the sum and difference of simpler rational functions which are more easily integrated. You need to know and be able to apply the rules associated with partial fraction decomposition. This includes performing polynomial long division when the degree of the numerator is the same as or exceeds the degree of the denominator. Once you know how the denominator factors, you have to be able to apply the rules of partial fraction decomposition to identify the number of fractions or the number of rational functions required and how many constants are needed in the numerators to complete the decomposition. And finally, once you have the simpler rational functions, you may need to apply trigonometric substitutions when a quadratic factor sits in the denominator.